So now, hello everyone. We are starting today's lecture number, as I remember, 4. We have today adjunctions and limits. I would say that they are one of the most fundamental concepts in category theory, and why the category theory exists itself. So when we are dealing with different branches in mathematics, we are trying to solve from time to time some universal problems. We are trying to move from to reformulate some problems. We are trying to see what approach in algebra can lead to the result in topology and vice versa. So this is all is encoded by category theory. It's one of the reasons why it exists. It is given a common framework for all these things, and generalizes and gathers all the properties, all the theorems that one need in life, that you won't be doing separately for abelian groups, separately for groups, separately for topological spaces, for homotopy theories, and so on. So this is precisely the core, what we are doing. Other concepts are more elaborated and they give some, I don't know, deeper thoughts, but the adjunction and limits are the two. So last time we finished with commas, and this allows me to start with the following definition. So the first part of the adjunction. We finished. Let L and R will be L and R are set to form an adjoint pair A for any object E in B. There is a natural azimuth. So what we are doing, we are taking image of object A under the factor L, its object in category E, and compare it with object B. We are taking object A and taking arrow from A to R of B. And these two home sets need to be isomorphic. Now it's very important to write where they live, the objects. Here objects live in category B. Here objects live in category A. And the natural isomorphism, let's call it capital phi AB, sub AB, yes, need to be natural in A and B, in both variables. In each separately and in both independently. In this case, we write that L A. Then I'm writing such special type of arrow. So arrow, but with a slight ending. B. So this formula, or just L to R, means that L is left adjoint and R is right. Or we can say that functor L has a right adjoint R, being left adjoint itself of functor R has the left adjoint, and so on. So anytime when you are reading something and it said something about the adjunction, that something has a joint or this, just to try to write down who is on which side. Because certain functors are said, this functor has right adjoint. It does not mean that it is right adjoint, it has right adjoint. So for it, it is, so it is left adjoint. Like, be careful. Okay, then what we will do, we'll have remarks. Remark first. If you remember, this set last time I denoted as L B superscript L A subscript B in a home set. Okay, and then RB. Okay, and then I can begin an I. Thank you so much. Yes. Yes, of course, not RB. A or B and B. So we have two values of two bifunctors. First bifunctor is B superscript L, and second bifunctor is L A sub R. So we have such a junction if and only B L the isomorphic functor to AL. And these are functors from A O. So if this factor, bifunctors are isomorphic, if and only L is isomorphic to Y. Later we will reformulate this in terms of profunctors. We will say that functor has a adjoint if the corresponding profunctor is representable or co-representable. So next, what is naturality? Naturality means the following: that for any arrow from A prime to A, call it arrow A. For any arrow from B to B prime, call it B. The following square commute. Here will be B, LA. Here will be B, L, B, right? Here will be A, B. Here is A prime. Our phi. Here's phi prime, B prime, and here we need to write what's going on with our function. So objects here, or not object, elements here to the set are functions or morphisms from LA to B. Yes. So every this morphism we need to turn into morphism to LA B prime. How does it go? Okay. Here, take here, LA prime, using arrow LA, from B to B prime, here using B, and here is our random arrows. Therefore, if we call this arrow F, then we have a rule that F goes to B, composition F, composition LA. That's how to move from one set of morphisms to another. And as you see, from LAB to L prime B prime, and A is going from A prime to A. Because the first is contravariant argument. First argument in home is always contravariant, because home is contravariant on the first argument and covariant on the second. Okay, so here is B, composition blank, composition LA. Here, of course, will be symmetric. RB composition blank, composition A. Very nice. Part 3 of the remark. Well, when we have, let's write it down, B LA comma B isomorphic to A. We have two special cases. Which special cases do we have? The case when here we will take, instead of B, LA. Why should we do this? Because we never know what other objects in category are. But we know that if there is always identity, so you can make a canonical choice. It does not matter on the situation, on the category, functor, or whatever. So always for any functor L, we can consider home set from LA to LA. And in case when it has right adjoint R, we will have corresponding something there. And we can look at the image of identity morphism here to that. So precisely what we think. So, equals LA. LA is the image of object A, not Los Angeles. So here G. Okay. Here it's phi. LA. A. Then here we will have identity on LA, and this identity on LA is going to phi A on LA, not both ones, just second one. And this thing we denote as eta sub A. By naturality, we obtain that eta is a natural transformation from identity factor on category, never remember, A to R. And this one, this natural transformation we call unit of adjunction. That's how it arises. If we take the same strategy and put on the right hand side instead of A, RB, we'll obtain. So here equals RB. We'll have G here, LRD comma B. Here is only function on the opposite directions phi RB comma B minus first. It's natural isomorphism one has inverse. Then we have A here. Here will be RB comma RB. Here we are taking identity on RB. And identity on RB corresponds to phi minus first RB comma B of 1 RB. And this value is called epsilon sub B. Then we obtain by naturality that epsilon is a natural transformation from L R to identity factor on category. And it's called co-unit. The junction was the co-unit. How I memorize how and write unit and co-unit? So unit, it's something real, it's identity. Co-unit is like imaginary, like number I in complex number, so it's something imaginary. And this is real. So from A to RL, RL, real life. And all I think is that I should go from identity to real life. So to real life goes unit. Here I don't know what is L R. So the opposite then is 4. This again. Our unit and co-unit satisfy the following two identities. So epsilon L L equals identity natural transformation on functor L, and R epsilon R transformation on functor. We have these two equations. I'll put here double star. On my initial statement about the natural isomorphism between form sets of star. Later will be triple star. And well, let's write down because it's a nice formula, but you can see without additional exploration. So I will write L composition the identity, natural transformation L R L, natural transformation to 1 composition L. Here is identity. Here is theta. And here is epsilon L. It's one triangle, and the other triangle is 1 composition R. R composition. And here R L R. Here is identity. Here is R. Here is R epsilon. So I just stated that these zigzag identities or equations, however, or triangle identities, triangle equations, pick up your own way to call them. They are stated in this way. So for you to see how it moves, how it goes. And it's not the same. So you can put them in one picture. Because here it's function R, here it's function L. You can do that so easily. Okay, then number 5. Number 5 is called universal morphisms. Universal morphism. What it says that eta A is initial in common category A comma R, and epsilon B is terminal in I wrote down trying to work. Okay, this is all nice word, but while until we'll see how it really works, so what does it mean to be initial, what does it mean to be terminal, we won't feel the connecting was not previously. So before this is just magic. Programming such formula would be called magic number or magic formula because it's from nowhere. It's like no explanation, no derivation, just something. Okay, and so what? No, everything needs to be named properly and linked to all the material. So how should we see this? That consider category A, R. So what are objects in this category? Objects in this category are arrows from A to image of R to image R. Of course, here is A, and here it should be copy of B. But I'm being right now a little lazy, so I'm writing just arrows from A to R. So A is fixed. And we have morphism eta A, eta sub A. What is it? It's a morphism from A to R, L of A. So it's a morphism R, and here is L of A. As you see, this is an object in the comma category. This is an object in comma category. For upper one, eta sub A, here let's call it G. To be initial means that here exists unique morphism, making this diagram to commute. But this morphism should be from alt AA to B. And here will be its image under R. So what it is? We are taking arrow from A to RB, G, and taking its image under phi AB. So here we will have thank you. So LA, B. Here will be G, let's call it G flat. It's not B, it's as in music. You have this thing. Other one is short. So moving to the left, I don't know. I'm doing all this. I'm putting flat. If I'm moving through a junction to other flat, I'm putting this thing. But you know that it's image, so phi minus 1 sub AB of G. So here this morphism is G flat, and here is R of G flat. So this one is fixed. And whenever I will have a morphism from A to RB G, there will be its left adjoint to that morphism, so moving through the adjunction from the right to the left, and its image under R is a morphism in a comma category. Similar story is in L comma B. So there in L comma B, we'll have LA. Here, let's take F to B. Here will be L, R, B. Here is epsilon B. And here exists unique L of F sharp, where LA F to B corresponds to A to R B. And here will be A. So it is phi and AB. Not phi minus 1, but phi. Well, that's it. Okay. Full statement. Honorable triple star. And now theorem. So let A here goes function L B. In opposite direction goes R. Defaults. Following are first. So the definition of adjunction in terms of natural isomorphism of form sets or isomorphism of functors. Second. Zigzag identities.
Stars.
Yes, star definition. Zigzag identities 2 stars and initial terminals 3 stars. So second equivalent is 2 stars. It means that there are natural transformations eta and epsilon such that triangle identities hold. And third thing, every comma category has initial and terminal object. Comma category, so A, comma R, and comma category L. It's a theorem about the adjunction. So you can state adjunction in any of these ways. So from one you prove another. So always you can make a third. So start from one point and get to other and vice versa. For you, if you want to practice a little in category theory, it's a good exercise to show yourself that starting from a scratch sheet, from a blank page, on a scratch sheet, you will write adjunction and derive everything yourself. So 2 stars and 3 stars. Then start from zigzag identities on another blank page and derive both adjunction and universal morphism. So who is universal morphism, you will ask me. So this eta A and eta B, they yes, they are universal morphisms. Because there is more general notion of universal morphism, it's related to universal property of limit, co-limit, whatever, even without it. We can state it later, but not now. So, and from initial terminal morphism, we also can derive everything. So that eta A it will be natural, epsilon sub be natural, for them hold zigzag equivalence. Or if they are so, and these are maps, then for these maps, knowing that these maps exist and they are unique, you will define that phi AB of will be defined as this map, this unique one. So you just have function pretty much of f. So function of f, you will call it f sharp. So phi minus 1 takes f to phi takes f to f sharp, phi minus 1 takes g to g flat. And then you also will need to show that it's natural isomorphism to do what? Go component-wise, check naturality, and that is inverse of each other. Phi AB and phi minus 1 of AB that are real inverses. It's a lot of dirty job, you will spend the whole day, but once you will do this, you will feel that your anxiety of all the things is gone. Just do it one time in life, and you will never forget this fantastic, tedious experience, and you'll be much less scared. I did it a couple of times, because I did 1 year, and forgot, and did another year, and did it again. So, it's as your dilemma. You should go through it. There is no other way. Just to your hands will remember writing things. Hands. Okay. Then a couple of properties and examples of adjunctions, and we are moving to limit scoring. Adjunctions you have seen many times. First time you saw it in the middle school. That's not a joke. And you can guess where it was. So who guessed where the adjunction was in the middle? Between what and what? Between expressions, when you were putting in expression is x, y, x, and something simplifying, put in this. And you were getting from expression of x, y, put in the x, expression of y. If you put the x, y sum, you get expression of x. This is an adjunction. Okay, convincing. Let's go in example. And then you did it again in calculus when you were trying to take limits in R2. You were doing it again. And many times elsewhere. So example first. So take x belongs to set. Then we have two functions. Length cross x from set to I put in immediately adjunction. Here will be set function. This is an adjunction. Let's go component wise. So set from A Cartesian product X comma B as a mode set A comma so what objects are here? Functions from x cross x. It's a function. So function of variable a comma x. And it takes values in. What objects are here? It's a function. Okay. 2, 7, x comma b. So f of a is getting a function from x. If you remember parameterization, you would say that a goes as a parameter. You have as a homotopy parametric family of maps. So this a is as your time parameter. So it's like f sub a. So your f sub a of x equals f. Here is your reduction. So once you have function of two variables, you are fixing one variable and getting function of the other variable. Magic. Vice versa. Once you have function that is set of functions parameterized by subset, parameter A, you can consider it is a function of two variables. One is your parameter A, another is your variable X. Second is free forgetful adjunction. Well, it's one asks, what is a forgetful function? Forgetful function is a function for which exists left adjoint called free function. What is a free function? It's a one for which exists forget the right adjoint which called forgetful function. So it's a paradigm. It's not something fixed, because you can have lambda modules, and you want to forget this left or right lambda structure, and you want to get the Abelian group. Right. If you have topological space, you can forget the topology and get just set. So here will be you can't say that it's for free forgetful that there is At one point there is a set. No, not that. There are so-called concrete categories. So concrete categories are categories for which there exists exactly a forgetful factor to the set. And that factor is called fully faithful or just faithful, I forgot. These are concrete. So all categories which we work, not all, but pretty much all, they are concrete. Then are groups, logical spaces, groups, who is this? Who else is? Partial order sets, no, partial order sets, not a poset as a category. Many of them, lattices, whatever you have. These all are concrete categories because there is underlying set, and between the sets we have functions. So concrete categories, I'm not writing about them, I'm just giving you a hint once you encounter them. Concrete categories are sets with additional structure, and morphisms between the objects so in concrete category are functions between sets with some additional properties. They preserve something, they reverse something, they do whatever they think. It should be continuous. So it's about the inverse image, operation, statement, and so on. So free forgetful adjunctions. I will say a couple as, for instance, we can name the modules. We have here factor U, and here are building groups. Here will be function F. Or just let's write, yeah, that will be it. So what is doing left the modules? It's pretty much it's a homomorphism of left lambda modules from lambda to blank. So homomorphism from lambda to blank are precisely codified by the abelian groups, which is underlying module. Because you will have your lambda structure will disappear on the left. Yes, there is a lambda structure on the right, which you're going to get out, but we're not thinking about that. What about free? Well, free is you're taking tensor product over the lambda. Lambda is a abelian group, so you're taking tensor product of abelian groups. Yes, of course, lambda will have lambda in its right structure. Another example. Another example will be the following. Well, that we have here. Here set, and here abelian groups. So from abelian groups U, we are forgetting the group of the operation, and here will be as I remember, usually free group is denoted as Z. Here, C. What else? Monoid. Here's the monoid. Taking the set, and here is taking the right curve here. Free monoid on a set. So you are joining empty symbol, or whatever it is, you call it its identity, and taking all the words. And concatenation of words, it will be a monoidal operation. Not monoid, it's an operation on the monoid. That would be correct. Well, the same with groups, but here you will have free group on a set. So we'll be taking all the words, subject to, that if two letters with inverse and without inverse meet, you cancel them, and whenever you will have this empty symbol in expression, you can just skip it. Logical spaces. Set. Here again will be U. What will be here? Discrete and discrete. Discrete. So every function from a discrete topological space to any topological space is continuous. And conversely, if you have a function between the set and between two sets, it can be made in a continuous function, assuming that your domain has discrete topology. Okay. Then, since I started with this free forgetful, I want to give another example. Well, actually, nobody needs it here, probably, except me, because I love it. But it shows a couple functors and couple adjunctions in one line. And that's fantastic. In this thing, you will see both free forgetful, co-free, and co-forgetful. So it is y0.
By the way, can you say anything nice if it happens that the function has both the left and right adjoint? Like here, that you're forgetting.
That it's bicontinuous.
Sorry?
That it's bicontinuous, it preserves limits and colimits.
Okay.
That's what you will nice have, but it's limits at next topic.
Okay.
So right now we are just stating that we can jungle with functors when we have a junction. So y0 adjoint just adjoint to all adjoint to discrete. Where does this functor split? So y0 goes from here to z. It takes category to set small category to set of its path components. If you are doing homotopy zero, it's zero is homotopy group. Then discrete is going from set to cat. Discrete category function. Then objects. You are going from cat to set. It's functor which assigns, which forgets morphism. Okay, this is a forgetful function. This is a forgetful. This is free. And the last one, indiscrete. It's indiscrete case. What is indiscrete category? A is leave 1, 2, offset from A1 2. So between any two objects, there is precisely one. Precisely one. From this follows that all objects are what? Isomorphic. Because if you have two objects A and object B, there is always a star function going from A to B and from B to A. But composition of A to B and B to A, it will be from A to A. But from A to A exists only identity. So from this, just know that all objects are isomorphic. Here is indiscrete set. And we have such huge line of adjunctions.
So discrete category means you just have the identity morphisms there.
Only identity morphism. So this one, discrete category, you can think about this as a this the simplest trivial graph on a set. Okay, so you take a set, all the elements of set are vertices, and there are no arrows except trivial loops. Here you are taking set, and on the set you are making complete graph. Remember what's complete graph? Between any two vertices there is precisely one edge. And you are saying that it's goes under the composition. Where composition of two edges is an edge between first and third component. That's it. Here is it.
Well, what else should they have?
A sigma omega adjunction. Sigma omega adjunction. So you consider homotopy category of topological point topological spaces, and you have functions omega of x. It's set of loops on a topological space X. But you are taking not just set, you will take set of homotopy classes of loops. That's why I'm going to H2. Otherwise, it won't be fun. Sigma X.
What is that? Top lowest star mean?
So it's homotopy category of pointed topological space. So in every topological space, you're picking up a base point, x0. So what we were talking about last time about pointed sets, now pointed topological space. And morphisms are continuous maps of topological spaces which preserve the base point. So it's a commutative. But you are taking homotopy category. What does it mean? That you are introducing the notion of homotopy on sets of morphisms and taking quotient of it by the equivalence. So you're passing through from continuous maps between pointed topological spaces to their homotopy classes. It's also a set, but its elements are not functions. They are classes. And sigma x, it is x smash. It's a smash problem. Oh, well, by the way, so in sigma, this adjunction has a special name that I never remember. But I just call it sigma omega adjunction. It's ubiquitous in homotopy theory and every related topic. You cannot see a page or a paragraph where this won't be used. It's an essence of spectral and not spectral of spectrums. Set of sequence of topological spaces form a spectrum if there are weak equivalences, and you use that sigma and omega. You have sigma spectrum, omega spectrum, it's infinite loop spaces, and go on. So it's algebraic topology used in on every single page. 6 will be 6. Well, is that something? Something. Let's call it power adjunction. I'm just giving it for the reason that I will be using it in tensor-home cotensor situations. What is it? I'm taking set A. Then, assuming that let's take not A, let's take X. That's a set. And A category with all products. Well, that's pedagogical mistake because for products I will talk in FFO or even less. But I want to state it already. Products and products. Now you'll see what they by the junction. So we have a factor s dot length of A going to A. Here will be x taken to power x. So this is f dot object A means co-product of A x so many times, how many elements in the set x. A superscript x product of set A so many times, how many are elements in the set x. Okay, this was about examples. And now, first was adjunction, second contravariant adjunction. Adjunctions, there are two contravariant adjunctions. So first A. B. Natural isomorph. So A. Where we have again A. That way is going L. Backwards to R. Both of these factors are contravariant. No. No, the factors are not the factors that just are. They are contravariantly adjoint. That's the point. You always can pass to the so take it instead of B op, and you'll get the usual adjunction. In this case, we have B sub L is isomorphic to A sub R as factors from B O cross A O, isomorphic to A O cross B O. The symbol is will have L from A, and here I will put on both sides the thing, and to know that it's right, I will put the arrow from left to the right, pointing to the right. B. I am author of the symbol myself. When writing my thesis, I need to write about left and right contravariant adjunctions, and I have no symbol. In literature, there is no fixed symbol; they just set. Or it's sometimes called dual adjunction or whatever.
So L and R are contravariant factors here, right?
They're
contravariant, but mutually right adjoint. That's what you want to say.
Yes. They're contravariant and they are joint in this way. Yes.
So I mean, I was saying more formally we think of L as from A op to.
You can always pass changing B by B op to usual adjunction. B left adjunction it will be L from a left contravariant injunction. It's an opposite symbol. B. Well, soon you will see them a lot. We are never thinking that there are a lot of them. Pretty much, I would say that maybe not every, but almost every adjunction what we encounter can be encoded by a triple of pairwise right or left contravariant adjoint factors. So everything goes to contravariant adjunction. Well, that's also a question. You will ask, what about unit co-unit? Well, when we have right, co-unit is the same. But unit well, of course, this impacts exact. I don't want to write this down now, no time. Well, in this case, left, the situation is opposite. So we have from LR to 1 sub epsilon. So a co-unit, it's the same, and unit going from real life to 1 sub A. Proposition. Let L A adjunction D R epsilon eta. By the way, when people write adjunctions and they want to talk about unit and co-unit, they also can encode them in this symbol. They can put epsilon co-unit on the top and unit on the bottom. That's how all heroes are getting in one team. And so every time I'm saying adjunction, I mean covariant adjunction. When I need contravariant adjunction, I have to specify. I must specify that it's right or left contravariant adjunction. Taking ops somewhere in the picture will always turn your left to usual, right to usual, and always you taking both ops, you can take right to left, left to right. Whatever is you take. Then A L is full if and only if that is component wise money. L is faithful if and only if there is component wise retracted. R is full. R is space. At the center, the section, series. For all of it. The functions are from E to A. Of category. If and only exists L from A to B. L is less than or equal to R, comma, F from eta, natural isomorphism. So our factor R is a joint isomorphism in this case, people say. Here is everything surprising maybe, but once you will get down again to home sets and who is moving whom from whom, you'll see. Okay. So the next topic today it's a big topic. We will start it today and finish next time. It's limits and colimits. So part 3 will be the called sum universal construction. Universal construction. One. What is one? Initial and terminal. Initial and terminal object. So for every x, unique from up my perp arrow from perp to x, terminal from any x to perp, there exists unique arrow. This is object of category A. This is object of category A. This is arbitrary. This is objects are fixed. We had it previously. Coproduct probe. So product and product of whom? Object x comma y. So coproduct. Now let's first talk about product. It's more natural, arises in every single person memory. So suppose you have set x and set y. Just think about sets. And we are taking any set A and considering any pair of functions. Any f, here any g. Our question, can we encode these both functions in through the isomorphism to the single object? We are taking Cartesian product of sets x and y, and considering projections phi sub x, phi sub y, and taking a morphism from a set A to xy. What is it as a diagonal morphism? So A will go to FA, square FA, G. And this morphism will go FG. In column. It's unique. This is fixed. This is a Cartesian product of sets. This is set x. This is set y. Projection on the first component, projection on the last component. Taking any A, taking any two functions, there is a unique function that will pass through this. Beautiful. So you can encode 2 through 1. And any f and any g and any a. Now forget the word set I said. Call them all objects and maps morphisms. This is a product of xy, and it comes with pair px in y. Maps canonical projections. That's our project. Co-product. You have set x, you have set y. And you are taking set b. Here is function f, here is function g. You want to also encode pair of functions with a common end through the single arrow. Then you are taking x, disjoint union y. Remarks for children: if x and y are sets that say, in your case, have some common elements, then just add labels to x, labels to y, and then mix them together. So what is a disjoint union? Put set x, put set y, just next to each other, as not mixing them, even if they're just next to each other. Potential is labeled if you need. We always have injection. Iora sub x, Iora sub y in this disjoint union. And then we can encode this to the function f g, with maybe without column, let it be comma, just to separate it horizontally. What does this function do? F will take x small to f of x, y small to g of y. So on the half that belongs to x, it acts as an f. On the half that belongs to y, it acts as a g. That's such function. Very well defined function. Now again, forgetting the word set, forgetting the word function, call set object, morphisms. So coproduct is a triple. X, coproduct y, Iora x, Iora y. Such that for every pair, there will be unique, and here is a unique arrow. Make it the diagonal. Again, I will put here any, next to be able to put any.
If you can coproduct the function f, g, would set that x and y to what?
X of this part is setting to be by function f, and y, which is alternative.
What is the result inside the
Because,
regarding the sets?
because f is taken from x to b, so they both belong to b, and g from y to b. They belong both to b.
Yeah, but so what? It's supposed to be an element inside the b, right?
Yes, it is. Always. So whenever you take, so you have here
Oh yeah.
like apples or oranges, but both you pay money. Think about the store. You go into the store, there are many objects. You're picking up that, this. But whenever you will take, you will pay for every separate using that price. And you'll have can I have a check, please? You ask. So it is number 3. It's co-equalizer and equalizer. And equalizer. You have arrows, two parallel arrows, F and G, between X and Y. Okay. So what does equalizer do? You are taking object E and math E such that F equals G. It's equalizer. If whenever I will take here A, go with there with the same property. Here will exist unique H, making the triangle commutative. And whenever for any A such that FA equals GA, there exists H such that A equals EH. That's a statement about the equalizer. In case of set, so comment. So if A is a set, then equalizer of find to be a set of all elements s x small in x, such that f of x equals g of x. It's a set where both functions coincide. That's why it's equalizer. For equalizer, you're taking x y, here's fg, and they're co-equalized by c to object okay. And whenever you have b, an arrow here b that co-equalizes g and f, here will be unique arrow h, make it a triangle. So c f equals cg, and whenever bf equals bg, there exists h that b equals h. It's a co-equivalent. In the case of set, for equalizer, equalizer of f of g, this I think it will be pairs by 1 by 2. Like classes pair. Such that there exists x equals x, such that y1 is I don't know. You can look up yourself, but pretty much it's we are taking identifying objects in Y that have equal images. And we are taking from f of x and g of x. So we are trying to identify and model elements that are getting equal under this. Not equal that are coming from the same element. I just don't want to read. Next, push out footer. Footer. Abbreviation PO. So you have diagram for footer. Y. You have arrows F and G. And you are taking object here P with pair of arrows. Let's call them X, Y. such that for any A that makes the outer diagram to commute, here will be A1, here will be A2. Between H, making both triangles commute. And in this case, I'm writing this corner such thing, which I told you already, it's about pullback. Push out. I'm considering X here. Out of X, that's D. Here goes to X. Here goes to Y. Here is F. Here is G. And here push out to the object Q with pair of maps. Here will be Iora X, Iora Y, such that for every E, arrows here will be B1, B2, will exist in H, making both triangles to commute. And here, where is Q, will be written the other type of thing. So in the case of co-equalizer, we will have co-equalizer, it's a pair C, comma, morphism C, equalizer, it's a pair object T, morphism P. In case of pullback, we'll have P, we'll have X, Y. Here we'll have Q, Iora X, Iora Y. I think all the things you have seen, and when you're going through the courses, you encounter them here and there. That's why I'm not going so much in details and so on. I'm just listing them. So every time what I do, I'm taking a certain object and bunch of morphisms going in this object or out of this object in a case pullback, in this object in case of push out, in, out when equalizer, in, co-equalizer. Okay. What about the initial terminal? Initial is per, terminal is copper, and without any morphism. You don't need it. So here is this one. So what do we do? Every single time. How much time we have? 7 minutes. Every time, what we do is the following. I'm having here something which is called diagram. What is a diagram? Some set of objects with arrows between them. I'm finding here object making a call. So dropping down arrow to every object in the diagram. So these are arrows. And this is object. Whenever I will take some other A with also arrows falling on the same diagram, there will be unique arrows from A to B, such that all arrows going out of A from the apex of a goal will be in fact just prolongations of arrows coming from P by this map H. For the other side, I have the similar. Here is my diagram. Here is my object Q. And to Q, I have a call. And anytime I have another call to some object P, there will be a factorization. So there will be a map from Q to P. Unique map H. What is a diagram? In case of pullback, it is this diagram. In case of push out, it is this diagram. In case of equalizer, co-equalizer, this diagram. In case of X and Y, product, co-product, what is it? Who will say?
It's just actually two
dots. So here's diagram is X and here's Y. Between them, nothing else. Just X and Y. Here, what is the diagram? Yes. Single dot, whatever. And then going in of it, out of it, or to it. Wait, nope. Nope. Diagram, it's where we are shooting to. So here, it's an object, and it's any, so it's H.
Yes.
There is no diagram. We just take in an object. And for any other object, they didn't have nothing to connect with. There will be an image. That's good that we made mistakes. Mistakes are good, we're learning from them. Diagram. Okay, 5 more minutes. Let's make a couple of definitions. And next time we'll go in very dirty details of personal life of our ladies and colleagues. What do they do? What do they do? Not do, never do. Okay, definition. J, I wrote script J, P is small case. A category. Once again, from J to C. Is called category of but sometimes nobody says the J. X diagram. So factor category from a small category is a category of J or J-shaped diagram. Category of that. Well, the diagram. So factors. C. Sorry. J. Such category. Okay. Factor G C is given by let's call them here 1 0. So let's give you 0 2 1. So this factor will be then f of 0 1 f of 2 and 2 arrows. So here is your diagram. It's a simple diagram, very simple, finite. Okay, for push out, similar. If you will have G equals just 2 dots, then you will have, like, first, let's call this dots 0 and 1 without any arrow user. So your diagram will be f of 0. Okay. So cone definition. Okay, next. Don't have time. So summarizing, today we looked in adjunctions in all the details from 3 sides. So how they are connected to common categories. We had examples of adjunctions. There will be much more. Everywhere where you look, you should look for adjunctions. And every factor, what you see, you should always ask yourself, does it have an adjoint? Every single factor that you see, you ask yourself, does it have an adjoint? And if yes, then what it is. How to recognize adjoints, we'll talk about next time. It's using the limits. Then we looked at diagrams of different shapes and universal properties of certain objects mapping to the diagrams, which are cones, the smallest, closest cone to our diagram through which everything factors will be universal cone or cocone, and object, this one, QOP will be co-limit to limit extent. So all this next time. Thank you for your attention. If you have any questions, you are free to ask me now, later, anytime. Bother me how much you want. So see you next time.